Oh, hello, old friend. It's good to see you. Let's talk about this word, fascination. It describes an unquenchable urge, which compels our hearts to quest and be captivated. As long as there are elegant explanations to complicated phenomena, science will never lose its romance. Over the years, I've traveled the world, indulging in my fascination in physics. And now, I find that a new hunger has woken within me. A fiery need to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicists podcast, and I'm Ben Tippett. And now, allez, physique! If I recall correctly, the ancient Greeks did a lot of astronomy, and we know how they imagined the universe was constructed. So at the center, there was the Earth, and above it, the sky, across which circled the sun and moon. And they recognized the planets. They imagined them as fiery wheels touring the sky on large circular tracks. In fact, the word planet means wanderer, because their motion contrasts with the rest of the stars in the sky, whose location with respect to one another was fixed. See, they imagined all of the other stars as being fixed, bright points on a huge black sphere that rotated slowly across the sky over the course of the year. Okay, so that was the universe as we knew it in antiquity, and since then, our understanding of the universe has changed dramatically. In my opinion, the largest revolution in our understanding happened near the start of the 20th century. Prior to the 1920s, our modern understanding of the universe involved only the Milky Way. We imagined the Milky Way as being an island of stars in the universe of darkness. Now, of course, astronomers could still see other, what we'd now call galaxies. They just thought they were clouds and nebula and other smudgy things. So, the man who opened our eyes to the universe, his name was Edwin Hubble. He was looking at a type of star called a Cepheid variable, and it's a type of star we called a standard candle. Now, the star in particular that he kept seeing was in what we now know as the Andromeda Galaxy. He figured out how far it was from us, and the answer is that it's very, 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 very far away from us. So far that it's well beyond the 100,000 light years of our Milky Way. Hubble's discovery opened up the possibility that our Milky Way was not just an island in the darkness, but rather an unremarkable cluster of stars in a universe blooming full of other galaxies just like it. Boom! The deal is that his discovery depended on figuring out the distance between the Earth and the Andromeda Galaxy. Now, how do we know how far away astronomical objects are from us? It's not a trivial question, and as it happens, astronomers have a whole toolbox of different techniques that tell us the distance to other stars. On today's show, we're going to be talking about the cosmic distance ladder. So stars, they're far, far away from us. And if we ever travel to other stars, it'll be really, really far trip. And going the distance is a really daunting task. Speaking of going the distance, our guest today is a world-famous web cartoonist who's just concluded his epic, heroic fantasy comic, which has been running almost daily for over 11 years. Dominic Deegan, Oracle for Hire, started in May 2002 and has been updating almost daily ever since. Welcome to our show, Mookie Terracciano.
Good to be back, man. You give me far too much credit for world famous. My head, I think, grew a couple of sizes.
So, Mookie, you've just started a new webcomic called Star Power. Do you want to tell us anything about it?
Yeah, Star Power is very different from Dominic Deegan. Near the end of the comic, I started to get a little more astronomical because I took up stargazing. So I was starting to lean in that direction anyway. So Star Power was just kind of the next step. It's about a young astronomer in the far future on a distant space station who gets granted the star power. She becomes the last of the star-powered sentinels, and now it's up to her to explore a galaxy that is both more dangerous and more wondrous than she could have ever imagined. You can read it at starpowercomic.com.
That's awesome. Our website will also link to your new comic. So, Mookie, today I have assembled for you 2 titanium physicists of note. They're amazing astronomers. So arise, Dr. Amanda Bauer. Dr. Amanda is in Sydney, Australia at the Australian Astronomical Observatory. She got her PhD from the University of Texas at Austin, and she studies galaxy formation. She is a notable public figure on the internet where she blogs under the name Astropixie. Now arise, James Silvester.
That's the worst TARDIS sound ever.
James is currently a doctoral candidate at Queen's University in Kingston, Ontario, where he studies stellar magnetism. Until recently, James was the manager at the Scottish Dark Sky Observatory, and he has a podcast called Astrarium, where he and David Warrington introduce us to astronomy. So, there's going to be a link to Amanda's blog and James's podcast on the Ti-Fi website for you. All right, everybody, let's start talking about distances.
There was a time when I was playing soccer and my coach asked, if you're waiting for somebody to pass the ball to you, you're supposed to stand about 10 meters away. And so he kind of made us do this little competition to see who could actually tell how far 10 meters was. And it wasn't really that easy. We were all pretty different in our guesses. And it made me start thinking from that time on, how far are things? You can kind of get an idea of maybe 100 meters or so, because most sports fields are about 100 meters. But then it gets more and more difficult to tell distances. We can only estimate to a couple miles. So for humans, telling distances on Earth isn't actually a very easy thing to do. Now, imagine if you're trying to do it at night. If you see some light off down the road, you have no idea if it's a person with just a flashlight that's pretty close to you, or maybe it's somebody on a motorcycle that's pretty far away. We can use little clues like the motion. If it's a car, you can tell that it's moving towards you, so the lights are getting brighter. But now imagine you're looking up in space and you see all these stars. Some look brighter than others, but you really don't know if the bright ones are because they're closer or because they're bigger and just intrinsically brighter. And people looking up at the sky have been thinking about this for a long time. The ancient Greeks were trying to think about the moon. How far away is the moon and how far away is the sun? It turns out that determining distances to things is actually really hard. And almost every astronomical theory that we have on any object out there is dependent on the fact that you know how far away it is. And yet, this is one of the most difficult measurements to make in all of astronomy. So one of the early tools that we use to try to figure out how far things were is this thing called parallax.
You have to remind me what parallax is. It's an eyesight trick, isn't it?
Exactly. If you have, say, something on a table in front of you and you cover one eye and you look at it and you look at where it is relative to all the other things in the background, and then you cover the other eye, you see that it actually moves a little bit relative to what's far away on the other side of the room. Okay. And so your eyes working together can give you a three-dimensional view of where things are relative to you by knowing that the Earth orbits around the sun. And we can use this idea of parallax. So when Earth is on one side of the sun, you can see a map of where all the stars are. And then 6 months later, it's on the opposite side, and you can see another map of where the stars are. So stars that are kind of close will actually move their position a tiny little bit based on parallax. So it'll look a little bit different.
Now, is this the natural movement of the stars because they're close to us, or is it like our perception of the stars?
Like, it's because we actually move to the opposite side of the sun that we see the nearby stars shifted just a little bit relative to what the background stars look like.
Yeah, it's kind of like when you look at like a forest, as you're walking past a forest. As you move past the forest, the trees move past you, right? But the ones that are farther into the background will move kind of slower than the ones closer. So they move relative to one another as we move around, just as a matter of the distance to us differs.
Right. But the amount of the star shift is pretty...
It's pretty tiny.
Yeah.
It's pretty tiny, yeah.
It's a tiny amount, and we can only...
like super instruments to like detect it, right?
Yeah. So the first parallax was actually measured in about the mid-1800s, and the nearest star is Proxima Centauri, and its parallax is actually really small. It's less than 1 arcsecond, and an arcsecond is 1 3,600th of a degree. So it's a teeny tiny little movement. We can only measure this for a few
that they'd
stars.
be able to measure that in the 1800s.
1 arc second is a parsec, right?
And a parsec's about 3.5 light years, or 3.25.
Yeah, so
Well, that brings up an interesting point. That's where the name parsec comes from. So the parallax of 1 arc second. They cut those down, and that's what parsec means.
Oh, neat.
So most distances that astronomers talk about will be in parsecs or thousands of parsecs, kiloparsecs, or even megaparsecs. And then when we go to the media, we translate that into light years, because light years just sounds cool, too.
It just sounds pretty neat. Yeah. Someone says parsecs, they start thinking of the Millennium Falcon anyway. So they were able to measure that crazy small amount of shift in the 1800s?
Yep. They had a telescope called the Hipparchus telescope, which did measurements of several thousand stars, and so they were able to make pretty precise measurements.
God, that blows my mind. I mean, I know how they discovered Pluto was they just took, like, 2 pictures of the sky, and some poor dude had to eyeball it. You know, comparatively, it's like, well, this looked like it moved. Hey, you're right, Planet X, yay! But, like, did they eyeball a couple of arc seconds in the 1800s?
Well, Tycho Brahe, who's a famous Danish astronomer, is famed, even to this day, is the one human that made the most accurate naked eye observation of stars, and it's claimed that he was getting measurements in about, in these sort of ranges of very sort of small measurements, and no one's surpassed him since, because soon after that, telescopes were created and invented. So I think Tycho Brahe still has the legendary status of being the most accurate naked eye astronomer ever.
Well, why would you go back to naked eye astronomy when you have all these, like, awesome telescopes at your disposal? Oh.
So a parallax was one of the first ways we determine distance to some objects, the very close ones, actually. But it's the only method that doesn't make any assumptions about what that object is or physically how that object works. So it's just based on the fact that Earth moves around the sun. It doesn't matter what you're actually looking at. You can only do it with stars, but it doesn't make any physical assumptions about the objects, as opposed to every other way that we determine distance has some basic assumption about the actual object that we're looking at. You can only use parallax to measure stars up to about 1,000 light years away.
That's still pretty good.
It's still pretty good, but then you consider that the Milky Way itself, our galaxy, is about 100,000 light years across. So this really is kind of our local neighborhood that we're measuring using this method. So in order to look at things beyond that, you have to start going to different methods.
Okay.
So as has been said, that parallax has this limit. So the next step out, so to speak, is standard candles.
Candle isn't like the thing that burns a...
Yep,
like
that you
light?
have in your birthday cake or that lights your room in a power cut. The name itself actually is a big clue with what it is. And essentially, the way to think about it is if you hold a candle, you have sort of an idea of how bright it is. And, if you give a candle to your buddy or a friend and they walk away, the further they get, the fainter the candle will seem to your eye. If you imagine that all the candles throughout the world were manufactured identically and they all burnt with the same brightness, you could look at any candle and with a bit of knowledge you could try and work out how far away it is by saying, well, it's so much fainter. So it's so far away. And this follows what's called the inverse square law. So basically, as you double the distance away, you quarter the brightness, so the brightness goes down. So this is the idea. You look for astronomical objects of which you sort of know something about the intrinsic brightness of this object, so you can use that information to try and discern how far it actually is from us.
It's more comparative, you pick a star that is like the standard, I guess, and you then compare other stars to its brightness and try to determine the distance?
That's essentially right. The thing that you have to be careful of is stars, they look like they behave normally and very consistently, but actually the more you study them, the more you realise they behave in different ways. You need to make sure it's a type of star where you know for sure that it behaves the way you expect it. It could be fainter for other reasons, not just because of the distance. So this is where we get the term standard candles. So this is not for all stars, this is for certain types of stars, and that sort of brings us on to Cepheid variables.
What kinds of stars do apply? I mean, are Cepheid variables the only stars that standard candle applies to, or are are there other ones?
No, there are other types of stellar objects, but Cepheid variables is one of the more reliable ones. And then as we go further out, you can start thinking about things like supernova, which we'll talk about momentarily. But the Cepheid variables is a reliable one. And the reason it's reliable is, first of all, its light intensity varies. That's why it's called a variable. If you look at the amount of light coming from it, it goes up and down with a pattern.
Is that what defines a variable star? That the light that comes from it is variable? Is it that simple an explanation?
Yeah, that's exactly it. And there's types of variable stars because there's different mechanisms which lead to this variation. But with the Cepheid variables, it's actually because essentially the star is pulsating, so it's sort of expanding in and out. And this is due to what's called the Kappa mechanism. The easy way to think about this is imagine a star and it's got a lot of gas inside and it's very hot and there's a lot of energy happening. What you're going to get is if you, for example, you put water in a saucepan and you start boiling it, what you'll see vapour and steam collecting, especially if you've got a lid on. And when you'll notice as time progresses, you start to not be able to see the water because you've gone from a cold liquid and it's getting hot and suddenly you've got this steam and vapour, so it starts to get cloudy. So what you have is a situation where these stars have got a lot of ionisation happening, so they're kind of cloudy. And this cloudiness prevents initially a lot of heat escaping, so they just get hotter and hotter. And what happens as a result, they just have to expand to allow this energy to sort of balance. Because when they expand, they get slightly bigger. This means it becomes a little bit more transparent for a little while. And that lets some of the energy escape, and then they collapse back down again.
How much does it expand? I mean, are we talking like a lot or like the super...
Well, we're not talking massive, like it gets 10 times bigger. It's sort of almost, it's a sort of pulsation. So
it's relatively subtle?
Yes. I mean, if you're close to the star, it'll probably be pretty obvious, but yeah, it's a subtle effect. But it's enough of an effect that it presents itself on the surface in a way that it sort of changes the light pattern and pulsation.
Okay.
The period can vary on the term of a few days to a few months, and it can get 100 times brighter and then 100 times fainter over that time. So it's called the period luminosity relationship, and it's because of how quickly it gets brighter and fainter. You can tell how intrinsically bright the star is, like how bright its internal candle actually is.
With how these stars fluctuate, since they can get like so much brighter or so much dimmer, is there a known, I guess, standard for them? Like, do they have a standard brightness, or are they just known to get dimmer and brighter? Or do they ever have like a regular time, I guess?
The pattern of brightness to darkness, let's call it, usually, if you consider a standard candidate for this type of work, it would have a regularity to this brightness, dimness, so on and so forth. So it's a repeating pattern. Amanda pointed out that then leads to this period luminosity relationship where you say, well, if it's got this pulsation period of 5 days, it must be this bright. If it's got a pulsation period of 10 days, it must be this bright. And then you basically have a really assured number for the brightness, and then you can use that to work out its distance.
Gotcha.
The relationship between the period and the luminosity as a process is kind of easy to intuit. One of the names for this K mechanism is, they call it the Eddington valve. It's kind of like, it's fun that James started off with an example of like a pot with water in it. So have you ever taken a pot and filled it with water and put a lid on it and then set it to boil?
Oh, quite.
And then what happens? Like, the steam builds up inside until there's enough pressure on the inside to blow the cover off, right?
I've never done that, but...
No, it doesn't blow off. It just lifts a little bit and you get a puff of steam out, right?
Right, yeah.
Okay, so essentially that's the same thing that's happening in the star. So essentially there's all these helium atoms inside the atmosphere of the star. The star is so hot that all these helium atoms have lost their electrons, and that means that they absorb light and bounce off light really easily. So light isn't traveling through this atmosphere very easily. So it's just like the pot with a lid on it. It's keeping the steam in. It's, all these photons are causing essentially a big buildup of heat. And then it's just like how eventually the heat on the inside gets big enough that it can pop the lid just a little bit off the pan and cause like a little puff of steam to come out. Eventually the heat inside the stellar atmosphere causes the stellar atmosphere to puff out. And as it puffs out, the helium cools and it can get electrons back again. So all the atoms in the atmosphere become slightly less charged here, so they interact less with the light. So suddenly all of the light can leave, just like when the lid's off the top. But that lid's still kind of hovering in the air briefly, and so as the temperature on the inside drops, the lid goes back down. And so what you do in the stove is you turn it on really high, and the lid goes clap, 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 really periodically, right? And the hotter you turn it up, the faster it's going to clap. Anyway, there's a relationship between how hot the stove is and how much steam gets released and the period of clap on the lid. Same thing with these stars. There's a relationship between how many photons get released, how bright the photons are when the star finally lets go, and how hot it gets, how heavy the star is. So this is what's causing the standard candle, the fact that this process has a nice relationship between the brightness of the star and this period. So we can measure the period using a telescope and a clock, or a calendar.
Right.
And then from there, we can tell how bright the star was originally. And we can compare the brightness of the star as we see it to the brightness as it was when it was originally, and we can figure out how far it is away from us.
Well, that's really cool.
So this method was originally calibrated by a woman in 1905 or so. Her name was Henrietta Leavitt, and she spent a lot of time looking at these fuzzy blobs called the large and small Magellanic Clouds. And so she cataloged maybe 20 or 30 of these things and came up with this relationship, and one of the best ways to be able to determine the distance to object. This is a very reliable method.
And it's still applicable like 100 years later?
Yeah, we can still use it. You just have to be able to identify the Cepheid, which you do by this variability, and then you can determine it. And you use it to calibrate other distance indicators.
That's great. And you said that Hubble was looking at a Cepheid variable in the Andromeda Galaxy?
So Hubble spent a lot of time in about the 1920s. He sat up all night at this telescope looking at these fuzzy blobs in the sky. And the one that he looked at a lot was Andromeda. And he would look at it, every month or so, he'd go and take another image. And he was really great at finding patterns in the stars and noticing when there was an extra bright spot. And you can see this old plate where he would mark off one and say, oh, this is a nova, a star exploded. And then it would fade away after a couple months. But he noticed that one of these spots that he had marked as a nova actually got bright again after a few months. And
really?
Stars generally don't explode twice. So he realized there was something up with this star, and it wasn't just a nova, but it was one of these Cepheid variables. So he got very excited about the potential, and he used Henrietta Leavitt's method to determine the distance. And at this time, in the 1920s, we thought that the Milky Way galaxy was the extent of the universe, 100,000 light years. That's all we got. So he used this method to determine the distance to Andromeda Galaxy because this Cepheid variable star was inside that nebula. Discovered it was 4 million light years away. So our universe goes instantly from 100,000 light years to 4 million. And all of these little fuzzy blobs that we see in every direction aren't just little nebulous things, but they're entire galaxies on their own.
That's crazy to me that this all happened less than 100 years ago.
Isn't it? Yeah.
It's still relatively recent information for us. It's wonderful. I love it. So was Hubble's first discovery of a nova not being a nova, but a variable star, was that the first variable star that was discovered, or had there been other ones, like in the Milky Way that we'd seen before?
Yeah, they had been in the Milky Way. So Henrietta Leavitt's catalog was for two very, very nearby galaxies, and then other ones in the Milky Way. So this was the first one that was confirmed to be in a distant galaxy.
Oh, okay. So part of the excitement was that he knew he was looking at a variable star somewhere else?
Yeah, exactly. It was in the
that's crazy.
Galaxy.
Oh, man. Can't imagine what he must have been thinking that moment. Like,
But yes, a lot of stars are variable, and then if we want to take it to a terminal variable star, that will be a supernova. And one that's particularly useful for distance determination is what's called the Type 1a supernova. And basically what you have here is this is a supernova explosion that's a result of a binary system. So you usually have two stars, one orbiting the other, and one of the stars is a white dwarf. The reason this is important is these white dwarfs are quite small, compact stars, and they basically, relatively speaking, have a small mass limit before they get very unstable. If this was a massive star, you could pile loads of mass on it, and it would be pretty happy. And what happens in this binary system, you have the white dwarf, and then you have this second star. And you get a situation where as the second star, maybe it's coming towards the end of its life, the white dwarf may start to what's called accrete material. So it basically starts to suck some of the material off the companions. And you may get a situation where it's accreted so much mass that it becomes unstable, and this results in a very energetic explosion, which is a Type 1a. Supernova.
So Type 1a is when the white dwarf explodes in the binary system because it's taken up more than it can handle?
Yeah, essentially. That's a very sort of basic description.
So, you know how the Earth's going to meet its end, right, Mookie?
Oh, yeah, the sun is going to swell up. It's going to become a red giant at the end of its life, and it's going to eat up Mercury, Venus, and Earth, and then it's going to shrink again, right?
Yeah, that's right.
Am I at least have that right?
Yeah,
You are absolutely correct. Yep.
Right.
All right.
So stars have life cycles. Essentially, they're big nuclear reactors. The nuclear reactions in the center of it are what power the star. You make it glow. They're what generate all the photons that heat up the rest of the star and make photons pour out the surface. Fantastic stuff. Anyway, that depends on kind of the chemical makeup of the reactions going on inside them, right? So the different types of elements fusing produce different types of energy. So helium reactions put out more energy, I think, than hydrogen fusion. As a star burns out of one type of element, it will start burning other elements, and that will cause the star to puff up, which is how the Earth's going to end. So the way these systems work is essentially there's two kind of older stars. One of them is a white dwarf, and the other one has just puffed up. And it's puffed up just like how the sun's going to puff up and swallow the Earth, only it puffs up and the surface of the star kind of enters the gravitational regime of the other star. So gas from one star is going to start getting sucked on to the other one. If I could jump really high, I could jump high enough that I would get stuck on the moon. Or maybe if I was on the moon and I jumped really high, I could jump high enough that I would get pulled onto the Earth, right? It's a similar thing. Stuff from the red giant is puffing up and getting sucked down onto the white dwarf. So there's a variety of chemical things. It turns out the end state of a star is kind of a subtle thing. If a star is light enough, then the gravity involved isn't enough to cause really heavy element burning. On the other hand, if a star is really, really heavy, it might supernova. And usually stars don't gain any more mass over the course of their life, so they start off one type of star, and then they'll burn through all their elements and et cetera, and then die in an old folks' home. These binary stars, because the mass is changing, because the chemistry is changing from this inflow, suddenly it can go from the type of star that won't be exploding. It can cross the mass threshold into the type of star that does runaway explode.
I see, and that's a type 1A.
Yeah.
So the reason these type 1A supernova are useful as standard candles or distance markers is basically these type 1As always have the same light curve. So what that means is if you plot how the light changes with time, it sort of rises to really bright and then over time it slowly fades out. Regardless of roughly speaking where this 1A explodes, it pretty much has the same curve. So what that means is essentially it almost has the same maximum luminosity. So you can treat, within reason, 1A the same as any other. So that means wherever they are, they're going to behave in the same way and have the same intrinsic brightness.
Now, are these usually seen in other galaxies, or have we observed them here in the Milky Way?
Usually in other galaxies, and if there was one relatively observable in our Milky Way, it might be quite concerning.
All right, these are great, these supernova 1As, because they're really, 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 really bright. And they're bright enough to see at really, 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 really large distances.
Like other galaxies.
Like other really, really, really far away galaxies.
Like galaxies that existed when the universe was about half its age.
Really?
And so it's fantastic because we can use them to figure out how the universe is changing in size over time.
Ah, very good. Yeah.
So there were two different teams in the 1980s and 1990s. So they were looking for as many of these supernovae as they could find, and they were trying to figure out how far away the galaxies were that they lived in. Mm-hmm. And they were using this to try to figure out how quickly those galaxies were actually moving away from us, under the assumption that the whole universe was expanding. They wanted to know how quickly the universe was expanding.
Okay.
So these two teams, independently, using supernova that they discovered, determined that not only is the universe expanding, but the universe is accelerating in its expansion, which is kind of crazy. Gotcha. And this discovery actually won the lead scientists of these projects the Nobel Prize in 2011.
Really?
Yeah. So the discovery that the universe is accelerating in its expansion was a pretty decent discovery, good enough to win the Nobel Prize. They originally published that in 1998, and they didn't get the prize until 2011.
2 years ago?
Yeah,
Jesus.
It's taken a while. But you have to verify that that the results are right and stand the test of time and all that.
Right. And they were measuring it by these supernova?
Yep, that's right.
Okay.
Incidentally, so the history of the expansion of the universe is really fun because this represented a new level of understanding how the universe worked, and it threw in something completely out of the blue that, Einstein predicted accidentally in the 1920s. So Hubble, we started talking about Hubble, right? One of the things he discovered is that the universe is increasing in size. And he did it using something really fantastic. He could look at other galaxies. He was looking at how the color changed. Last time we were on, we were talking about special relativity. Do you remember?
I remember, yeah.
Okay, so in special relativity, if something's moving towards you really, 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 really fast, it changes the color.
This is Doppler, right?
That's right.
Like blue shift and red shift?
That's right. It's the analog. It's the special relativity analog for the Doppler shift. Mm-hmm. So if you're moving towards me, a white light will look bluer. The same way, your car will go when you're driving towards me and driving away. So the if you're moving away from you, the white light will look more reddish color. So we call those red.
But this is moving at very, very fast speeds that we noticed this, right?
That's right. Yeah.
Like if you're running at me with a flashlight,
yeah,
I'm not going to notice, before he hit me with the flashlight, I saw a blue light. Oh, shit.
That's right. So what Hubble did was he looked at the colors of galaxies that were fairly far away from us, and he could figure out how far the galaxies were using these standard candles. Is that right?
He didn't use standard candles. He used their redshifts, essentially. He measured the hydrogen that was coming from stars. If you've got some hydrogen that's coming from a star in a distant galaxy, that hydrogen light kind of travels in a wave. And what that little hydrogen wave doesn't know is that the universe is actually stretching around it, and it's stretching the wavelength so it's a little bit longer, so it becomes redder. So by the time that hydrogen light reaches your eye, it actually looks redder. And so he measures this little hydrogen notch in the spectral rainbows of all these galaxies, and how far that hydrogen shifts to the red is how long that light has been traveling, and therefore how far away that galaxy is.
Oh.
So he figured out that every single galaxy, except for Andromeda and our little neighborhood...
Which is coming right for us.
Yeah, exactly. Every single galaxy is redshifted. And the really crazy thing is that the farther away the galaxy is, the faster it's moving away from us.
That's still something my brain still has trouble wrapping around, and I love that simple fact is just so mind-boggling. I just get a kick out of it.
All right, so imagine you got a couple ants and you put them on a balloon. Let's say put 3 ants. So one at the North Pole, one at the South Pole, one at the equator. Okay. You start blowing up the balloon, and we can talk about the distance between the ant at the equator and the ant at the North Pole, and the ant at the South Pole, and the ant at the North Pole. And as you inflate the balloon, the rubber is stretching kind of evenly throughout the balloon. Right. What happens is the distance between the ant at the equator and the ant at the North Pole is increasing, same as the distance at the bottom and the North Pole. But also the speed at which the distance is increases as you inflate the balloon.
Gotcha.
So it's like space itself is expanding in these, intergalactic regions. And so objects aren't moving farther apart. It's that the distance is actually increasing, like it's on the surface of the balloon.
Gotcha. I did hear that once before. Thank you for reminding me. It's still a neat analogy. I think it's great that we're in a big universal balloon.
Well, it's a 3-dimensional balloon instead of a 2-dimensional. I mean, the surface would be 3-dimensional instead.
Right. Yeah.
All sorts of.
I hope we're shaped like a dog.
So this type of universe is consistent with one of the early predictions from Einstein's general relativity. So yeah, in 1905-ish, he wrote a whole bunch of papers that revolutionized physics. This is when he was like a patent clerk. And it was called his miracle year because he published all these crazy papers that revolutionized everything. And then he spent the next, 10 years of his life trying to perfect a theory of gravity that used his special relativity laws. And this theory is called general relativity, and it's the theory of gravity that predicts things like black holes. So one of the things his model of gravity predicts is a model of the universe, where if you assume that matter's pretty evenly distributed over the universe, and you want it to be evenly distributed because if you clump up too much matter in one place, it'll suck itself down in and make a little pocket of a gravitational well. So you make sure that the universe at the start is really, really uniform, matter's evenly distributed, and you'll find that what happens is, you can make it expand, and what'll happen is, in these early models, the ones that essentially Hubble ended up confirming, is that they expand uniformly, and they'll keep on expanding, but as the effect of gravity pulls these massive objects apart, it slows down It's like the universe started off with a bunch of momentum, so it's slowing down as it stretches out. And then so what happens is, depending on how much momentum it has originally, the universe can either recollapse or it can keep expanding forever. And it might recollapse in form of big crunches, right?
I've heard of the big crunch, yeah.
Right. So what the discovery of, by looking at these supernova 1As, is what we could do is we can get a much better handle on the history of how the universe has been expanding over time. So we can have a sense of how this expansion has changed over time. And we had expected that it would kind of be slowing down as time went on. But what we see is that it's speeding up as time goes on. Because these supernova 1As give us a better sense of the history of the universe as it expands, we can see that way billions of years ago it was expanding at a slower rate than it currently is today.
And they can figure that out just by looking at type 1As?
Yeah, that's right.
And measuring the distance?
That's right. It gives us a profile for how the universe is expanding. And what we can do is we can figure out what type of matter is in the universe. And it turns out that there's like 70% of the matter in the universe is this weird thing called dark energy. And nobody knows what dark energy is, but it's ripping everything apart. It's a magical thing. All right, that was wonderful. Well, absolutely fantastic. So thank you, James. Thank you, Amanda. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Amanda, you get the latterest of all fruits. It's a banana.
Yay, my favorite.
All right, James, and for you, I brought in a star fruit.
Nom 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 nom. Pointy.
All right. I'd like to thank my guest, Mookie Terracciano. Thanks, Mookie.
Thank you for having me, Ben. This is always a great time.
Good work on finishing up Gomic Deegan. Good luck on Star Power. All right, my TIE fighters, listen to me. I love the show. I hope you do too. But for every listen to the show, I know that there's 100 other people who would love to listen to the show, but they don't know how. So I want you to spread the word. There's 3 ways you can do this. The first is iTunes. It's still the place that everybody goes, even though the iTunes app is kind of crummy. Go to iTunes, write us a review if you haven't already. Each review puts us closer to the top, and more people will find out about us. The second way is to teach people how to listen to podcasts. Listen, everybody's got a smartphone these days, or an iPod, or an iPad. Listen, most of those people don't know how to listen to podcasts. I don't know why, but they don't. So, tell them to download the Stitcher app. In fact, show them how. It's very easy. You go to the Stitcher app thing, you download it, you enter your name, and you can listen to all sorts of podcasts and subscribe to them. Subscribing is the best thing about podcasts because it does it automatically, and you can week after week listen to your favorite shows as they update. So it's free and easy to use, the Stitcher app, and it works on every handheld device. And also, when you're up there, you tell other people to listen to our show. So fantastic. The third way to spread the word is to tell people online about us. I've been seeing that people have been doing it as a fantastic thing. But the internet is full of people who want to know more about physics and are trying to explain it to each other. So if you see somebody who wants to know about us, or maybe there's a news article about some topic we've covered, tell them about the show. People will be happy and it'll drive new listeners to our show. So that's it. I hope you'll help us out and point new listeners in our direction. So that's the main part of today's show. Remember, if you like listening to scientists talk about science in their own words, you might want to listen to other shows on the Bracculate Media Network, like The Weekly Wienersmith, where Kelly and Zach Wienersmith talk to academics about their research, or Science Sort of, where we talk about science in the news. Editing support for the Titanium Physicists podcast is provided by a gentleman named John Heath. Thanks, John. You do a bang-up job at making us sound better. The intro song to our show is by Ted Leo and the Pharmacist, and the end music is done by John Vanderslice. Until next time, my friends, have a nice evening, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
That can't be right, because it's closer than it's like a light year and a half away, right? Proxima Centauri?
Proxima Centauri. It's 4 light years.
Yeah, and then 1 arc second is a parsec, right?
So the distance corresponding to a parallax of 1 arc second is 3 light years. Oh, yeah, you're right. That doesn't actually make sense. No, that's right. So it's about... Yeah, that's right.
That sounds about right.
So if the distance corresponding to 1 arc second, and this is just a little bit less than an arc second.
Yeah.
And a parsec's about 3.5 light years, or 3 1/4.
Shouldn't it be more the closer... it should have a larger parallax the closer it is to us, shouldn't it?
Right, exactly. And Proxima Centauri is about 4 light years.
Oh, it's 4 light years away. Oh, crap, I'm never getting there. Fuck.
Join the club, man.
All right, carry on.
Oh, well.
Hey, Mookie, I've got to tell you about Tycho Brahe after we finish recording.
He's a good cat.
Oh, about his golden nose and that stuff.
Pet moose, right?
Yeah.
Moose, really?
He died because he didn't want to ask to go to the bathroom, and so his bladder exploded or something.
Are you kidding me?
There's actually quite a bit of controversy over that, isn't there?
His bladder burst over a party.
Yes.
He was having dinner with the king, and so he didn't want to ask the king if he could get up and go to the bathroom.
I think this is one of the
courtesy.
reasons.
It wasn't trying to break the seal. It was just royal courtesy that killed him. Oh, man.
One of the reasons Kepler is one of my favorite astronomers, because he had to deal with Tycho Brahe as a boss.
Just ask to pee. It's not a big deal. No, I'll be fine. Oh, well.
Wow. So, where are we? So, one thing I wanted to point
Sorry to
out...
derail the conversation.
I think it's important to point out that actually a lot of stars are actually variable. Not Cepheid variables, but variable. And there's multiple reasons for that. Some are just variable because there happens to be some, for example, a planet passing in front of it making a light drop. There's the stars that are variable because they have clouds of chemicals in the atmosphere that pass and reduce the light or increase the light. So there's all sorts of stars that are variable for very many reasons. But obviously the Cepheid variables has a one that works particularly well for distance determination because it's consistent.
Okay.
And you can relate the luminosity to another parameter. And the reason that this is important is, we've already described that if you know how bright something is, if you take it further away, it's going to get fainter. But the difficulty is, are you looking at a big star far away or a smaller star close? And that's where things like Cepheid variables is good because you get information about luminosity separate from just, that sort of assumption. You get a sort of a second cursor to the luminosity, if that makes sense. So that's why they're so important.
I mean, please correct me if I'm wrong. Supernovas are clearly very bright if we can see them from other galaxies. Would it be of great concern to us if a Type 1a supernova were to happen, like, on the other side in the Milky Way? Still very observable to us, but, would it still affect us?
It's not going to affect us. So when a supernova explodes, it is brighter than an entire galaxy for a period of a month or maybe 2 months, depending. So they are really bright, and they put out a lot of energy. But you would have to be actually pretty close to the Earth in order to affect it. We have this really great atmosphere, which protects us from most of the radiation that the supernova would put off. So unless it was within, a few hundred light years, then it would be okay. So we've seen supernova explode. 1987 was a big one. So that was a supernova that was in our galaxy. And
Wait, really?
A fun fact, Betelgeuse...
1987?
Yeah, it was huge. It was,
what?
Yeah, that was...
I was alive then. I didn't hear about that.
Oh yeah, it was the first supernova confirmed using neutrino observations.
Yeah, exactly.
Because we were
and
bombarded by
we've
these neutrinos, and so the very early neutrino detectors heard of it.
And since then, we've been able to observe it and watch its little shell expand over the years, which is pretty exciting.
Okay. We didn't actually see brighter than everything. It was
no. I mean, you could see it with telescopes. I think you probably could see it with your eye, but it just kind of looked like a bright star at night. It wasn't like a
Oh, okay. So it wasn't like brighter than the full moon, change everything. So
Now, what would be cool is the star Betelgeuse, which is part of Orion.
I'm waiting for that one. I'm hoping. Like, come on.
So this thing can explode as a supernova anytime now, and if it does, it will be visible during the day for about a month, which would be...
That's going to break my wife's heart, though. Orion is her favorite constellation, and as awesome as that would be, like, she would start to cry knowing that her favorite
one
constellation...
star in Orion, everything else would be okay.
Oh, no, she likes the whole thing.
Yeah.
Trust me.
I'm with your wife, man. That star
Like
is the only consolation for wandering around in the winter in Canada.
She loves it. She loves it. She's attached to the damn thing. Like, she says hi to him at night more than me sometimes. Like, oh, I know you're going to be here. You're going to be here in the summertime. He's not going to. I have to go talk to Orion.
Yeah, me too. It's like winter and I'm cold and it's like 9 p.m. and I'm walking home freezing to death and I look up and there's old Orion sitting on.
Yeah. So I'd be excited for Betelgeuse to go. I'm just waiting, like, you're a supernova. But then I know afterwards, I'd have to hear it, like his head is gone or whatever the hell part of the Betelgeuse is. I don't know, his arm, shoulder, his elbow, it's his shoulder. He'll be fine.
But even so, if it does explode, physically we'll be fine on Earth. It's something like 600 light years away. We'll be okay.
Excellent. Now, if things derail, just blame me. It's probably me. It's probably me.
Well, it doesn't matter if things derail because I edit it, right?
Oh, excellent! All right, very good.
Yeah. I might be shaking my fist at you in the future, but no, none of these derailings are too bad.
Hey? Oh, come on! I'm not trolling your podcast.
No, it's good. Listen,
at least not on purpose. I might be doing it by accident. I don't know.
As long as you're having fun, it's good.
I'm having a blast, man. I'm having a blast.
As opposed to the regular supernovas, which are just type 1s?
Type 2s.
Type 2s? What's a type 1? Is there a type 1b?
Yeah, there are. Those are closer to type 2s than type 1a is the special one with the white dwarf.
Okay. So yeah, you're right.
It's a crazy numbering scheme.
I know, right?
Yeah.
It's like there's one type, and then someone decided to make a prequel.
Well, that's exactly right.
By the way,
the more you study them, the more you notice subtle details. You have to separate them into different categories and give them more uncreative names. That's essentially astronomy summarized.
Yeah.
They got to hire some writers in astronomy, man, to give shit like really cool names.
Oh, please!
This is a dark star supernova. Yeah. Oh man, that'll sell some books.
So,
one of the candidates for dark energy, actually. So Einstein, when he first found this theory that said the universe was expanding, he didn't like it. Philosophically, Einstein wanted a universe that was static, that was standing still, where galaxies weren't pulling away from each other. Because it's weird. You imagine this classical man thinking, philosophically, that's crazy. So he inserted a term into his equation that wasn't in there originally. And mathematicians have decided since then that his extra term is okay to have inserted. It's kosher to have inserted this term. But back then he was like, well, I'm just going to shove in this term. Because what this term let him do was it let him make a universe that stood still, that wasn't expanding. And he liked that. But then, the next year, Hubble came out with his discovery, and he was like, oh, snap. Adding this term, he was like, adding this term is the biggest blunder I've ever made. So this extra term, it's called the cosmological constant. It's known as Einstein's biggest blunder. But here's one of the neat things. The accelerating universe that we've just discovered, one of the candidates for the reason it's accelerating is that maybe it's that term Einstein added to his equations. Maybe it just has a value that's causing the universe to accelerate out. So it turns out his biggest blunder was 100 years.
It was like a prediction, like an accidental prediction.
An accidental prediction that was right 100 years later.
Right, but he didn't like it.
No, well, yeah, that's right.
No, he didn't. He didn't like the fact that hey, we're inflating. Well, I don't like that. Everything's constant. Yeah. Well, everything's constantly inflating, Einstein. Bugger. Shit.
Well, this was a pretty big argument, even into the some physicists were arguing, no, it's the universe always has been, it always will be, it's as it is, and others were fighting for the expanding universe. So Hubble found out that it was expanding at a constant rate, but they wanted it to just, not be accelerating or not have a big bang, just a steady state of the universe.
But that's wrong, isn't it?
Yeah. But this
They were
controversy
arguing
was
this in the 50s?
yeah, it had been around for a while. There were some people
30
that
years
were
later? It's like-
really holding on to their.
But you can see these galaxies running away, and a galaxy's not a tiny thing. It's fucking huge. Like, look, they're all getting away from us. This is not a subtle thing, guys. Like, we're not making this up. We've been arguing this for 30 years. Come on.